Characteristics of linear functions. Now that we know how to graph linear functions and write linear functions, we're now going to talk about all of the different characteristics of a linear function. So our objective is to identify the characteristics of a linear function. Okay, first, our linear functions can kind of be divided into two categories, increasing or decreasing. And we can talk about, often we talk about whether they're increasing or decreasing on an interval. What we mean by interval is just a small set of the domain. Okay, so if we just look at a small set of the domain, okay, we look to see whether it's increasing or decreasing. So to talk about increasing or decreasing, I'm first going to graph a linear function, and I'm going to graph a linear function with a positive slope. Okay. And it's no coincidence I put this over on the increasing side. So when I say on an interval, what I mean is if we just look at this graph, let's say from the point 6 to, let's say this is 10 out here. So basically what we're doing is we're just looking at this graph from here to here. So we're just looking at this spot right here and asking, what's it doing? Okay, and since we read a graph from left to right, the same way we read words, we look from left to right, and am I walking up or am I walking down? So if you're walking up from left to right, it is increasing on that interval. Again, we would just be looking for, like, what about from 6 to 10? What's it doing? Okay, so it's increasing on that interval. So it's increasing if it goes up from left to right. Again, because we read graphs the same way we read words, from left to right. Basically, a more exact definition is if these x's, let's say this, we didn't know this was 6, we'll call it A. We didn't know this was 10, we'll call it B. There's going to be an output value for A, f of A. And there's going to be an output value for B, f of B. A function is increasing if f of B is greater than or equal to f of A for any B that's greater than A. Okay? So meaning, as my x's get bigger, my y's need to get bigger too. That's all this is saying. Is here my x's are getting bigger if B is bigger than A. So if my number here is bigger than this one, then the output has to be bigger than the output for the smaller number. That's all that means. Okay, so that's the mathematical way of describing increasing. The non-mathematical way that's easier to remember in your head is it goes up from left to right. Okay, so in our linear functions, our increasing functions are going to have that positive slope. Because we know positive slopes go up from left to right, so they're going to be increasing. Okay, so then a decreasing function on an interval, again, is going to be that one going down from left to right. So the more formal definition for that is, again, we have this value A, this value B. There's going to be an f of A and an f of B. You're going to have an output for each of those inputs. If f of B is less than f of A for any B greater than A, so if we get smaller, if we go down from left to right, okay, then it's decreasing. And again, a lot of times we look there on that interval. Okay, so I want you to go ahead and do your turn 1. Think about this question, jot down your answers on your notes. All right, so we talked about one characteristic of functions is talking about whether they're increasing or decreasing. Another characteristic is talking about its end behavior. What the end behavior basically means is, what does the function do? What does the function do In other words, the outputs do. As x gets really big or really small. Okay. So, and we have a mathematical way of saying, hey, as x gets really big. So we would write it this way, as x, and then we draw an arrow, and then we draw the infinity symbol. So this basically means, and we read this as x approaches infinity. All that means is as x gets really, really big, what does this function do? And then we talk about x getting really small. We write it this way, x approaches a negative infinity symbol. I have a hard time with my infinity symbol. Sometimes it helps to turn my paper sideways and write an 8. I tend to do it as 2 zeros like that. Negative infinity. So again, this we would read as x approaches negative infinity, or gets really, really small. Because as we approach negative infinity, it gets really small. And as x approaches infinity, that gets really big. So we're wanting to know, what is the function going to do? Or what are the outputs going to do as my x gets really big? Okay, or as my x gets really small. So if we look at this function right here, f of x equals 1/2 x minus 3. So I can tell that this is going to be a linear function, mx plus b, with a slope of 1/2, a y-intercept of negative 3. Okay, and since my slope is positive, it's going to go up from left to right. That's always good to think there. Identify the domain of f. Okay, so this function doesn't represent any real life situation. So I can put, basically, if I graph this, I'm not officially graphing it, but it's going to go left to right for forever. So that tells me my domain here is all the real numbers. So I can put any number into here, meaning I can put in 5, I can put in 1/3, I can put in a negative, I can put in 0. You try the positives, the negatives, 0, and then all the in-between numbers. Like I can put in 2/3, I can put in 5.5. So the domain here is all real numbers. Is there a largest value in the domain? Meaning, is there an end point for my x? Meaning, am I going to only go over so far and then stop? Well, no, this is going to be a line. It's going to go forever, left and right. So is there a largest value? No. There's no largest value of x. It's going to keep getting bigger and bigger and bigger and bigger. Explain your reasoning. Okay, what's my reasoning here? I can always put a bigger number. Can always put a bigger number in for x. Or the graph goes right forever. Meaning there is no end point where it just stops going to the right. Okay, so now we need to talk about what is the end behavior as, look here, this is as x approaches negative infinity. That's a negative infinity, so that's as it gets very, very small. So negative infinity, okay, if I was to, I'm not going to graph it, but if I was to graph it, negative infinity would be like to the left, right? Because as x goes to negative infinity, negative numbers go this way, and x is going to get really, really small. What's happening to this graph as we go this way? Well, we know it has a positive slope, so it's going up. So as I go to the left, my graph is going down. What numbers are down? Positive or negative numbers? Negative numbers are down. So I would say, what is the end behavior? So I would say the function f of x goes down negative infinity as x goes to negative infinity. So there's how I would write it. My function, this is just saying, basically this is the mathematical way of saying, my function goes down as my x goes to the left. As x goes to the left, my function goes down. We're going down. Okay. So what about the end behavior now as we go to positive infinity? So that's getting really big. So that's going to, so here we're going to the right. Here, small, we were going to the left. So on this function, as we're going to the right, what's happening? My function's going up. So we would say, hey, my function, f of x, is going up. Positive numbers are up. F of x goes to infinity as x goes to infinity. So here my function goes up as x goes to the right. As my x gets bigger, my function gets bigger as well because this is an increasing function. Okay. How would the end behavior change if the function were defined as f of x equals negative 1/2 x? If you notice now, the slope is negative, so that tells me it goes down. Okay, so how will the end behavior change? Well, the end behavior is going to switch. Okay, it's going to switch since f of x is now decreasing. Okay, so what we mean by switch is now we're going down. So my function, my f of x, is going to go up as x goes to the left. Because as I go to the left, my function now is going up. My function now, my function now is going up as we go to the left. And f of x, f of x approaches negative infinity as x goes to the right. So basically what happened is this and this switched, since now we're going down instead of up. Okay, so now I want you to go ahead and jot down your turn number 2. What are the possible end behaviors of f of x equals mx plus b? So again, that's our linear function. What are our possible end behaviors for that? Are there only certain possibilities, or are there an infinite number of possibilities? What can you end up getting out? Explain your reasoning. Next, so we talked about, okay, so characteristics of functions. We talked about increasing and decreasing. We talked about end behavior. Another characteristic is zeros. So a zero of a function, a zero is any x value. So again, that x value is the input. Okay, such that f of x equals 0. Again, so this 0 is the output. So basically, it's any input that gives you an output of 0. So what x gives a y of 0? There really shouldn't be a comma there. What x gives a y of 0? Meaning, what do I put into this function to get out a 0? Or I'm looking for what x value gives me a 0 for y as far as ordered pairs go. Okay, so we're going to look at, there's a couple different ways of getting to those zeros. One is you set the function. If you're given a function equation, for example, if I'm given this one, and that's one of these examples don't talk about here, is if I'm given it as an f of x. So I'm going to fit this in the margins over here, guys. It won't fit. So if I'm given it as a function value, like if I'm given the 1/2 x minus 3, and I want to find the zeros, I take this function rule, which is 1/2 x minus 3, and I want to know what x makes this function equal to 0. Because I want to take f of x and set it equal to 0. So my f of x equals this. So I set that equal to 0. And we solve from there. So I'd like add 3 to both sides. So I get 1/2 x equals 3. And then I would divide both sides by 1/2. If I take 3 divided by 1/2, I get 6. So my input of 6 gives me an output of 0. So the 0 is the 6. X equals 6 is the 0 because it gives me an output of 0. What input gives me an output of 0? So if I'm given a function rule, this is how you do it. Okay, now let's look if I'm given a graph. So here, how can you find the 0 of f? What is the 0? So here is my function. There's my f. If you notice, it's got f right there. So there's my function. How do you find the 0? Basically, I want to find the point blank 0 on the graph. Okay. So I'm looking for where is the y value 0? Well, my y is my up and down. So I want to know where is my y 0? So that's going to correspond with that x-intercept. Basically, I'm looking for find the x-intercept. Because at that x-intercept, my y is going to be 0. So if we notice, my x, it crosses the x-axis right here. That point right there. And that looks at, if we notice here, we're counting by 2 for counting by 2's. So that would be at x equals -2. So my x-intercept is there at, I'm recording, -2, 0. Okay, so my x-intercept is at -2. I'm recording, okay. All right, so my x-intercept is there is -2. So if we're looking for it from the graph point of view, we look for that x-intercept. Okay, so next here we have a function g, which is a table. So we want to find the x-intercept, the 0 from the table. So I'm looking for what input gives me an output of 0. So basically I just try different inputs until I get an output of 0 right there. So try different. So how can you find the 0 of g? Find the input or x with an output y or f of x of 0, which is right there. So my 0 for that is 10. So there's my two zeros, x equals -2, x equals 10. Which function has the greater 0? G of x has the greater 0. 10 is greater than -2. G of x has the greater 0. Okay, so now your turn number 3. Does a linear function always have a 0? So I want you to think about all the different types of linear functions and ask yourself, will they all have a 0? Explain your reasoning. All right, so we have one last thing to discuss. Pretty sure. Oh, sorry, making it dizzy. One last thing to discuss here, characteristics of function. So we talked about increasing or decreasing, end behavior, zeros. Now we're going to talk about minimums and maximums. So a minimum is the y value. So a minimum is a y value. Okay, our zeros were x values. Our minimums and maximums are a y value. The minimum is the y value of the lowest point. On the graph of a function. Okay, so a minimum is the lowest point. A maximum is the y value of the highest point on the graph. So the y value of the highest point on the graph. So if we look at, here we're going to look at two separate functions, f and g, and we want to find the domain, the range, and then the maximum and minimum. Okay, so first let's go ahead and let's look here at f. So first we want to find my domain. My domain is my x values, or how far left and right this graph goes. If you notice, these are endpoints. This graph stops here and here. So my graph is not going to go any farther left than here at -5 and no farther right than 5. So in words, if I want to write the domain in words, for this one, sorry, I would write my domain. In words, I can say all numbers between -5 and 5, including -5 and 5. Or I can write it using my combined inequalities. So I could say, okay, x either has to be greater than or equal -5. So that's greater than or equal to -5. So that'd be numbers from here on up. And x has to be less than or equal to 5. Using the and symbol, or I can write it this way. Negative 5 is less than or equal to x, which is less than or equal to 5. That was our conjoined inequalities. So basically my x's are in between. This is saying that same thing. My x's are in between negative 5 and 5. The equal signs mean I'm including them. So you can write it in words if you'd like. You can write it in symbols if you'd like. So any one of these three would work. So you can write it in words like this. You can write it using the word and, or you can write it using that composite inequality. So there's the domain. So now my range. My range is how far, my range is my y, so that's how far up and down. So I'm going to switch highlighter color and we're looking at how far up and down does this go. Again, we have endpoints here. There's a high point. It doesn't go any higher than the 7.5. And it doesn't go any lower here than this negative 7.5. So again, for range, we're looking at the y's or the f of x's. So for my range, again, I could write it in words, all numbers between, so basically any real number between negative 7.5 and 7.5, including, you have to say whether you're including, yep, including negative 7.5 and 7.5. Again, or I can write it using these conjoined inequalities, 7.5, and since this is range, and we're talking about functions, I'm going to go less than or equal to f of x, less than or equal to 7.5. Okay, so again, this is, since we're talking about functions, instead of a y, we use an f of x. Okay, so there's the domain and range. So it has a high point, it has a low point. So now we need to find the maximum and the minimum. The maximum is the y value of the highest point. This does have a highest point. The highest this graph goes is up here. So my maximum, so I would write my maximum is 7.5. Again, that y value of the highest point. And my minimum, it does have a lowest point. Minimum is negative 7.5. It does have that lowest point that it goes. Okay. All right, so next we have, sorry, that was all for F. We now have to do G. Kind of out of room. Should have gave a little more room. We'll just write it over here onto the graph. So here we're looking at G. One thing to notice, these do not have endpoints. They have arrows, meaning they go left forever and right forever, and this graph is going to creep up forever and down forever. So the domain and range for this, the domain is all real numbers because it goes left and right forever. And the range is also all real numbers, so it goes left and right forever. So the domain and range are both all real numbers since we have no endpoints, left and right for forever. Since it goes up and down forever, it also has no minimum or maximum. It has no max and it has no min because this graph is going to slowly creep up for forever. Okay. All right, two last problems. Sorry, guys. All right, so here we have